So,
No. Okay,
Andrzej Okołów, we talk about Hilbert space. Please.
Okay, thank you very much. So those Hilbert spaces will be built over set of metrics of the same but fixed signature defined on an arbitrary manifold. So let me begin by the following observation. So given manifold, there are at least two Hilbert spaces equipped with Diffeomorphism invariant inner product. So one of them is the Hilbert space of complex half-densities on M. We know that such a density can be integrated over the manifold with in a Diffeomorphism invariant manner. And the other Hilbert space is the space of all square integrable functions of the manifold, integrable with respect to the counting measure on this manifold. This is very, of course, very simple measure, but still it can be used to define such a Hilbert space. So I will present two Hilbert spaces which will be denoted by this H and this K, such that each of this space will be built over the set of all metrics of fixed but arbitrary signature, which are defined on an arbitrary manifold, which means that this manifold can have an arbitrary dimension and an arbitrary topology. Product on this, the inner products on these Hilbert spaces will be Diffeomorphism invariant. And this space H will be a generalization of this space of complex half-densities. So in fact, this space will be built of some half-densities, while this space K will be a generalization of this space here obtained by means of the counting measure. Regarding potential applications of this construction, so let me note that the configuration part of the IDM phase space is the set of Riemannian metrics defined on a three-dimensional manifold. And therefore, one may try to use these Hilbert spaces, either H or K, obtained for the signature 3,0 to canonical quantization of the IDM formalism. What I mean here is that these spaces may serve as a kinematical Hilbert space for this formalism, for this quantization. And in fact, this application was the main motivation, my motivation for this construction. So first I tried to find a space of quantum states for this signature, and then it turned out that the construction is general in the sense that it works well without any essential modification for any signature and for any dimension.
But that does not allow for the change of topology.
The topology is fixed.
Yes, so that's why in quantum gravity, I imagine that also the metrics that are based on I don't know, free sphere, free tonus should be in a sense included in all possible.
Well, of course, that would be nice, but this construction is not so general.
That's not the general quantization of the metric over any manifold.
Yes. That's right. And of course, the diffeomorphism invariance of the inner products may be helpful in taking into account the diffeomorphism or vector constraint at the quantum level. So similar constructions are known from quantum gravity. But But unfortunately, neither of these spaces is an L squared space over the set of metrics, and it is not obvious that these spaces may be really useful for the quantization of the IDM formalism, and therefore some further research is needed to answer this question. So let me now present the idea of the construction. So to construct these spaces, I will fix a manifold and a signature PP prime such that the sum P plus P prime is equal to the dimension of the manifold. Now I will denote by this Q of M the set of all metrics of this fixed signature defined on this manifold M. And of course, it would be nice to have a Diffeomorphism invariant measure on this space, but as far as I know, no such measure is known so far. Therefore, I will use some other method to obtain these two Hilbert spaces.
What's the assumption about the metrics? Are they non-singular or anything is possible?
No, they are not singular because they have fixed signature. Right?
Singular,
This is the number.
Yeah, but whether it can go to zero,
Good.
like the coefficient in front of dt squared can be.
No, here I assume that all these metrics are properly defined over the whole line. So probably you can extend this because in fact, as you will see, okay, so there are no examples of manifold with some special topology properties, such that given a signature, this set is empty. Right? But still, this construction can be done even if the set is empty. So in fact, it is not so important whether this set contains that singular matrix or not.
So it can be something like a very narrow throat, for example.
Yeah.
And manifold is included. Okay.
So you can include. I assume that this set contains smooth metric, but it is not necessary. So now, I will use this symbol gamma x to denote the set of all scalar product of this fixed signature on the tangent space at the point x to the manifold M. And now, suppose that we have for every point of the manifold a measure mu x on this set. Now, using this measure for every x, we can define such a simple Hilbert space over this set, and then we can try to merge all such Hilbert spaces into a large Hilbert space over this set of metrics. But I would like this large Hilbert space to be equipped with a Diffeomorphism invariant inner product, and therefore it is reasonable to assume that this assignment, which I will call a measure field, that this measure field used to obtain this large Hilbert space is Diffeomorphism invariant. So now I would like to explain how I will construct such a Diffeomorphism invariant field of measures. Okay, so let theta be a diffeomorphism of M, and assume that this diffeomorphism maps a point x2 to a point x1. Then the tangent map, which will be denoted by theta t, maps this tangent space to this one. Now, this sets of scalar product, each of them is the set of scalar product on the corresponding space here. So, using this using this tangent map, I can pull back scalar products defined on this tangent space to scalar product defined on this tangent space. So this is this pullback. And now if I have a measure W x1 defined on the set gamma x1, then I can push forward this measure to a measure on this set. Okay, so now I will say that the field, this field is diffeomorphism invariant if the following equation holds for every point of the map. And now it turns out that this, for every, of course, for every diffeomorphism, right? For every diffeomorphism. So this is very strongly required. In fact, so suppose that a diffeomorphism preserves a point x0. Then its tangent map at this point x0 is an element of the linear group over this linear space. And now this formula in this particular case read as follows. So now we can see that what does it mean? It means that this measure on the set gamma x0 should be invariant with respect to this action of this linear group. So the conclusion is that if this is a diffeomorphism invariant field of measures, then each measure for every x must be invariant with respect to the action of this group. And now there is a question, does such a measure exist? It is not obvious. Okay, so it turns out that this set of scalar product, together with the natural action of this group, is a homogeneous space. Unfortunately, there is a theorem on existence and uniqueness of so-called quasi-invariant measures on homogeneous spaces. Unfortunately, it turns out that this theorem guarantees that on this homogeneous space there exists an invariant regular and polar measure. Moreover, this measure is unique up to a positive multiplicative constant. So this is exactly in the case of a higher measure on a group. And we know that all, for example, left higher measures on a Lie group are proportional to each other. So this is exactly the same. Okay, so this theorem only guarantees that such a measure exists, but it does not say how this measure looks like. And of course, it is nice to have an explicit formula for such a measure. Fortunately, in this case, it is easy to construct such a measure explicitly. So, first of all, assume that these gamma ij are components of scalar products in this space given by a basis of the corresponding tangent space. So in fact, these are functions on this space. And using these components and components of so-called invert scalar product, I can define such a tensor field on this space, and it is possible to prove that this is an invariant metric on gamma x, invariant with respect to the action of this group.
Don't you subtract bases in the sense that you change indices gamma ij contracted with d gamma ij?
It's okay.
No, but I say the position of indices can be different than this one. Yeah.
These indices,
You can.
ij and ij here.
No, usually one uses so-called big G ijkl, which is what you have written, minus gamma ij gamma kl. So there's a subtraction. Usually this capital G is used as a,
so to use
as a
one
metric.
single
Minus
index instead of
spaces,
two
minus
indices.
spaces.
Yes, it is
Usually,
possible,
yeah.
but in a way you will see that I will use it, but just to define this metric, it was natural to use this index. Of course, these components altogether they do not form a coordinate frame on this set because they are dependent, right? But now, if you restrict these indices in the following way, then these functions form a global coordinate frame on gamma x, and of course it is convenient to label this coordinate by a single index, and then if these qij are components of this metric in this coordinate system, then such a standard formula provides, in fact, an invariant measure on this space. So every invariant, the regular Borel measure of this space is proportional to this one. Okay. So now we already know that on every gamma x there exists an invariant measure, and we have an explicit expression for it. So now I would like to construct a Diffeomorphism invariant field using this measure. So suppose that this Lxx prime is any linear isomorphism between these two linear spaces, and I choose any point x0 of the manifold and any invariant measure on this set gamma x0. Then I can use such a linear map to push forward this measure from the point x0 to the point x. And it is not difficult to show that the resulting measure, the mu x, is invariant measure on this set of scalar products. Moreover, this measure is independent on the choice of this linear isomorphism. You can use any other to obtain the same measure. Moreover, if you have any 2 points, x prime, and any linear map between the corresponding tangent spaces, then the following formula holds. And in fact, this formula means that this measure field is Diffeomorphism invariant, because this linear isomorphism can be given as a tangent map given by a Diffeomorphism which maps this point to this one. So this field is Diffeomorphism invariant. So now one may ask a question: how many fields of this sort do we have? So not many. In fact, you can use the uniqueness up to that positive multiplicative constant of this measure to show that if you have any 2 fields of this sort, then there exists a positive number such that for every x, the following formula holds, right? So this number is the same for every point x. So in fact, you have only one family of such Diffeomorphism invariant field of measures.
One parameter family.
One parameter, yes, one parameter family. Okay. Now, let me come back to the construction of that large Hilbert space from this spaces associated with the points of the map. So how to merge them into that large Hilbert space? So now, of course, I assume that all these Hilbert spaces are given by a Diffeomorphism invariant measure field. And I will also use here the inner product on these spaces, which will be denoted by the symbol. Now, I will consider such a set. It is, I can say that it is a bundle-like set. Perhaps it is even a bundle. There is a notion of a Hilbert bundle over a manifold, but I didn't check whether this set satisfies all requirements, because I didn't need that. But in fact, we can say that it is a bundle-like set. Because of the structure of this set, we can consider section of it. So suppose that psi and psi prime are section of this set. Now, we can pair the value of this section point by point using this inner product. As a result, we obtain a complex function on the manifold M, and then we can try to integrate this function over the manifold.
But it is non-separate, yes? Because you just add Hilbert spaces point by point. You don't
Yes.
continuity or whatever.
Okay. So as I said, I will construct two Hilbert spaces. One of them will be not separable, and the other one will, I manage only to show that in some particular case the other space is separable, and I suppose that every such Hilbert space is separable, but so far I didn't manage to prove it. So now, of course, because I would like to have a Diffeomorphism invariant inner product on that large Hilbert space, so I would like to integrate this function over the manifold in such a manner, in a Diffeomorphism invariant manner. So, of course, I can use the counting measure of this manifold, because this measure is Diffeomorphism invariant. And using this measure, I will obtain one sort of Hilbert spaces. I can also, in a sense, densitize this function. So I mean here that I will, in a way, transform this construction in such a way that I will obtain not a function, but a complex density. And we know that the integral of a complex density is Diffeomorphism invariant. So in this way, I will obtain the other sort of Hilbert spaces. And since this construction is more difficult, I will present this construction first. Okay, so here I will introduce a notion of
psi and psi prime are chosen once and for all. Psi and psi prime are chosen once and for all for the whole section of the.
Okay, so of course you have many sections of this bundle-like set, and now the question is which one should be chosen to obtain a Hilbert space, right? So it is not that I'm not able to define such a Hilbert space using all sections. So I will have to choose some for one sort of Hilbert spaces and for the other sort.
But you assume that this section can be globally chosen for the whole manifold.
They can be, yes, because you see here I don't assume any smooth or something or continuous structure of the set, and therefore there is no problem with global sections, right? But in fact, I will in this case I will not use global sections, or we will see them. Okay, so what are half-densities valued in a Hilbert space? So let me start by the basic definition. So suppose that V is a real vector space of finite dimension and alpha is a real number. So what is an alpha density over V valued in a vector space W? So I consider the set of all bases of V And I consider a map from this set, which maps bases to this to elements of this vector space. And now this W tilde is an alpha density if the following equation is satisfied. Here, a basis of V is transformed by a non-singular matrix to another basis. So this formula I have to hold for every line, for every non-singular matrix. So this is a general definition. So now I will assume that this W is a Hilbert space, and this alpha is 1/2. So now these guys here are half densities valued in a Hilbert space W. And this Hilbert space is of course equipped with an inner product. And this inner product can be used to define a kind of pairing of these half densities. And the definition of this pairing is here. I can, given a basis of this space V, I have one value, one vector in this Hilbert space, another vector, and I can calculate this inner product of these two vectors. And it is not easy to, it is easy to realize that this map is a complex one density over V, complex, which means that it is valued in C. So in fact, this map here maps two half densities into one density, one complex density, and I will call this map a density product. Okay, now suppose that we again have this Hilbert space Hx. So I can consider the set of all half densities over this tangent space, which are valued in the Hilbert space Hx. And this set is equipped with the density product, which will be denoted by this symbol. Now, I can consider a section of the bundle next set, which is a sum of the sum of all such sets of half densities. And I will call any section of this sort, I will call a Hilbert half density. Because to say that this is a half density value in the Hilbert space is a little bit too long. Now, if I have two such half densities, then I can pair them using these density products point by point. As a result, I obtain a complex density of the structure. Okay, then I can try to integrate this density over the manifold. So, but of course, the problem is that for some Hilbert half densities, this integral may not exist. So now there is this question: how should I choose this Hilbert half densities to be sure that this scalar product is well defined? So an obvious answer may be of like this, that we should use half densities of finite norm with respect to this scalar product. Unfortunately, I didn't manage to prove that such a set form a Hilbert space. Perhaps it does form, but it was a little bit too difficult for me to prove. So I will proceed in a different way. So I will choose a set of sufficiently regular half densities, and then I will be able to show that this formula here defines an inner product on this set of sufficiently regular Hilbert half-densities, and then I will complete this set to a Hilbert space by means of the standard procedure. So now I would like this complex density to be continuous and compactly supported, because then that integral, of course, exists, right? So now I will try to impose some restriction on this then half densities in such a way that the resulting complex density is continuous and compactly supported on the manifold M. So now suppose that U phi is a local chart on this manifold. Xi, the corresponding coordinate system, and gamma is an element of the set gamma x. So if I have such a Hilbert half density, then its value at this point x is an element of this set of half densities over this point. Now, if I put here the basis of the tangent space over x given by this coordinate frame, then I obtain an element of this Hilbert space, which more or less is a function, right? It's in fact an equivalence class of functions, but I will neglect this sublet here. So if I put here the scalar product, then I obtain in this way a complex number. Therefore, I can define the following function, which its argument are the coordinates and components of those scalar products in such a way. Here, this point is expressed by means of coordinates, and this scalar product is expressed by means of the components. So I will call this function coordinate representation of this Hilbert half density. And in fact, this representation, this coordinate representation, contains all information about the half density on this set, because it is easy to formulate the formula which given which allows you to write this half density in terms of its representation. And I will say that psi is continuous if for every local chart on the manifold F, its coordinate representation is continuous. But this is not the end of the story, because the continuity and compact support of this of two half densities is not sufficient yet for our goal, which is formulated here. So some other requirements have to be imposed on this half density. So, okay, so to impose these additional requirements, let me fix a continuous Hilbert half density. And now its coordinate representation given by a chart allows me to define the following function. So this is the function defined only on the components of the scalar product. So now I will say that this Hilbert half density is of compact and slowly changing gamma support with respect to this chart if the following sum is contained in a compact set. So here I have a support of such a single function, and I consider such a union of these supports, and here the value of the coordinates runs through the image of of this set U. So now each guy here is by definition closed. And if this union is contained in a compact set, then each support is contained in a compact set. And because this is a closed set, then it has to be also compact. So this is why I say here that this side is of compact support with respect to this chart. And why slowly change? Well, look, all these supports have to be contained in one compact set, which means that if I change the value of the coordinates here, this support cannot suddenly become very, very large or just change suddenly too much its position in the space of component. Okay, and if I am able to cover the whole manifold by charts like this one, then I will say simply that the Hilbert half-density psi is of compact and slowly changing gamma sum. And it turned out that this requirement, together with continuity and with compact support on M, is enough for our purpose. Okay, so I use this symbol to denote the set of all continuous Hilbert half-densities of compact and slowly changing gamma support and of compact M support. Then it is possible to show that for any two elements of this set, the resulting density is continuous and compactly supported on M. Why is that? So, roughly speaking, this is a complex half density, and you can also consider its coordinate representation. Now, this coordinate representation is given in fact by the following integral, which is nothing else but the inner product on the Hilbert space Hx. And now, these functions here can be, this integral can be expressed in terms of these functions. And owing to this property, you can apply the Lebesgue-dominated convergence theorem to show that this integral is continuous with respect to xi. Therefore, this coordinate representation of this density is also continuous. And because these two guys are of compact M support, then the resulting complex density is also compact M support. Therefore, this density is integrable over the manifold. So the conclusion is that okay. Of course, it is necessary to show that this set is a linear space, and it is possible to do this. So this linear space is equipped with an inner product and is a pre-Hilbert space. To get the Hilbert space, it is enough to complete this space with respect to the norm given by this inner product. So in this way, I obtain a Hilbert space, which will be denoted by this H1. So this H1 is a generalization of that Hilbert space of complex half densities on M, but it is not yet the generalization H of this Hilbert space, which was announced in the introduction. Why it is not? So given metric Q on M, its values at two distinct points are independent. So therefore, we have to treat those Hilbert spaces as a representation of independent quantum degrees of freedom, and therefore it is reasonable to require that a physically acceptable Hilbert space contains tensor products of this function. But here you don't have any such product like that, because this guy is something like an uncountable direct sum of these Hilbert spaces. And therefore, this space alone rather cannot be used for any quantization. So I have to extend this construction in a way which takes into account tensor products of these Hilbert spaces. Okay, so now to do this, I consider the set of all n elements subset of the manifold N. Let me emphasize that this subset are unordered. It is possible to show that this set is a manifold which is locally diffeomorphic to the Cartesian product of n copies of n. So the difference between this set and this set is that here the n element subsets are ordered. Now I can use the same measure field, which was used a while ago, to define for every point of this new manifold a Hilbert space which is naturally isomorphic to this tensor product. Now I can repeat the whole construction. Some necessary changes are, there are some necessary changes, but they are not very essential. And in this way, I obtain a new Hilbert space Hn, which is built of Hilbert half-densities on this manifold. So now I have to merge or glue all these Hilbert spaces Hn into one. So perhaps the most simplest way is to use such an orthogonal direct product, which to certain degree is similar to the construction of FUW spaces. Right? Okay. As I said before, I would like the inner product of this new Hilbert space to be diffeomorphism invariant. So let's take a closer look at this issue. So if theta is a diffeomorphism, and if it maps the point x to the point x prime, then, as before, this is the tangent map given by this diffeomorphism. This is the corresponding pullback, which maps one scalar products to other scalar products. And now this Hilbert space and this Hilbert space are constructed over the corresponding spaces, and I can use this pullback to define another pullback, right? Which maps the Hilbert space Hx to the Hilbert space Xh prime. Okay. So suppose that I choose a Hilbert half-density on this simple Hilbert space H1 and the basis of the tangent space. So if I have this density, then this guy here is a number which is associated with the point x prime, because this is x prime, and this is a basis of this Hilbert space. So if I act on it by means of this tangent map, then I obtain a basis of this tangent space. So this is an element of this Hilbert space Hx prime. So I can use the inverse of this map to produce an element of this Hilbert space. So it is reasonable to treat this as a definition of a pullback of a Hilbert half-density. And it is owing to the diffeomorphism invariance of this measure, it is possible to show that this pullback defines a unitary map on this Hilbert space, and this assignment, in fact, is a unitary representation of the group of diffeomorphisms. So this is how we can get such a representation of this Hilbert space H1. What about the other Hilbert spaces Hn? Okay, so suppose this guy here is a point of this manifold, which is just a collection, a set of n points of the manifold n. So we can use this diffeomorphism to transform every element of this set. And it turns out that this map is a diffeomorphism of this manifold Mn. And using a formula similar to that which was shown a while ago, you can define a pullback of a Hilbert half-density defined of this manifold here. And it is not difficult to prove that, again, this pullback is a unitary map, and this assignment is a unitary representation of this group on the Hilbert space Hn. So we can take now all this representation and produce a representation of this diffeomorphism group on that large Hilbert space H. Okay. Another nice issue, nice property of this Hilbert space is that it is, in a sense, unique. So suppose that I got another Hilbert space by means of the same procedure, but that assume that I use another diffeomorphism invariant measure. So what is the relation between this Hilbert space and this Hilbert space? So let me recall that two diffeomorphism invariant field of measure are related by such a simple formula, with the number C independent of the point X. And then it is easy to convince ourselves that such a simple transformation here define a natural or distinguished unitary map between the Hilbert space Hn and this one. So this Hilbert space was used to obtain this H and this to obtain this Hilbert space. So now we can use all this map to obtain a distinguished unitary map between these two Hilbert spaces. And in this sense, we can say that the space H is unique up to natural or distinguished isomorphism. Okay, so now let me close the discussion of this Hilbert space, and now I will shortly tell you how to define that large Hilbert space, which will be constructed by means of the counting measure of the manifold M and by means of counting measures on that manifolds M. Now I consider again the bundle-like set, which is the union of the Hilbert spaces Hx, and I consider a set K1 defined as of sections of this bundle-like set, and this set is defined as follows. So psi belongs to this set if and only if the following integral is phi. Here we have the counting measure on the manifold M, and this guy here denotes the inner product of the Hilbert space Hx. So this integral can be treated as a norm on sections of this bundle-like set. So I just choose this K1 to be the set of all sections of finite norm. Now it is possible to show that this K1 indeed is a Hilbert space together with the inner product defined by a similar formula. And the other Hilbert spaces Kn can be built using sections of similar unions, which are in similar sense square integrable with respect to the countermeasure on the manifold Mn. And again, I can define a large Hilbert spaces by means of this orthogonal sign. And this is the generalization of that space L squared, which was announced at the beginning of the talk. Okay, let me now tell you about some other properties of these spaces. I hope that it is not a surprise for you if I will say that on this new space K, also there exists a unitary representation of the diffeomorphism law, and that again this space is also unique up to some distinguished isomorphism. What else? It is easy to show that every Hilbert space K is non-separable. And regarding these Hilbert spaces H, I managed to show that two Hilbert spaces built over a real line are separable. Why? Because here this is one-dimensional manifold, and you have two signatures, 1, 0 and 0, 1. So I suppose that every Hilbert space H is separable, but so far I didn't manage to prove it in a strict way. And of course, there is this very important open question: is H or K obtained for signatures 3, 0 applicable to canonical quantization of IDM formalism? So far, unfortunately, I don't know the answer. Some time ago, I constructed a representation of so-called affine commutation relations for the IDM formalism on this non-separable Hilbert space K. And I even thought about this. I presented this representation during the recent conference of the Polish Society on Relativity. Unfortunately, sometime later, I realized that this representation is unfortunately highly reducible, which means that this is not a good property from a physical point of view. So far, this question is over. So let me finish the talk by presenting two references. So in this paper, you can find the detailed construction of these two Hilbert spaces, and in this paper you can find the proof of necessary proofs and fact regarding that invariant measures and that Diffeomorphism invariant field of measure on the manifold.
Thank you very much.
I would like to ask, maybe it's a very good property that on non-separable space you have commutation relations which are reducible, because maybe then you can have something that will be equivalent to a separable space with non-reducible commutation relation, because with non-separable space it's very difficult to deal with.
Yes, I agree, but the problem is that it is really highly reducible in the sense that those invariant spaces are really very, very small. Each such space is related related to a finite number of degrees of freedom.
It's really less,
Yes.
less that you would
It's
expect
really
for a
high.
separate.
Yeah.
I see.
This is really high reducibility.
Okay,
That's the
okay,
problem.
okay.
Of course, it was not so much reducible,
Then it would
that
be
would
okay.
a good
Yeah.
solution.
Yeah.
Yes.
Some other questions?
Yeah, I would like to ask, if we consider metrics of different signature than Euclidean, then they don't necessarily exist on a given manifold.
Yes.
So what happens with your construction then?
Nothing, everything works because in fact I don't use metrics here. I use, look, everything works because I don't use metrics, I don't use any smoothness or continuity requirements. What I use only these spaces of scalar products, which are defined point by point. So I don't assume any connection between them. So everything works for any manifold, regardless this set here is empty or not. Okay?
But is
Okay.
it,
Thank you.
but so there is no relation to the metric, only signatures.
Yes, yes.
Yeah.
Yes, because I fix signature and I consider such sets for every point of the manifold, but there is this requirement that these are scalar product of this fixed signature.
Yeah, but is it good or bad not to have any relation to the metric?
But the relation is that if you consider such a set of metrics, then given point x, you can consider the value of the metric at this point, right? So the value of this metric is an element of gamma x. And if this set is not empty, then it is possible to show that the set of values at x of all metrics is precisely this set. So this is the connection. It is more or less like that construction of use of the Hilbert space, the kinematical Hilbert space of quantum gravity, right? That you have some, except those smooth connections, you have some distributional connections, right? So this is a little bit similar. So you don't have to consider smooth or continuous metrics. You can just sets of these values. You can in fact consider any.
Yeah, but your metric is a section of this, say, bundle of this scalar products. Yeah.
Say that is.
You can treat metric as a section of a bundle.
Yes.
With,
Yes.
Mm-hmm. So
With some properties like continuity or smoothness. Yes, sure.
so can you do something with this section in your structure?
So in this construction, I don't assume anything about the section. So
Yes, but the positivity of psi bar psi, when you have psi bra and cat the same, it is independent on the signature.
of course, because
Yes. That's why it is not relevant whether it is
Yes,
plus or minus,
yes.
because that will be positive anyway.
yes, it is positive anyway because the positivity is guaranteed by the scalar product here, and this is by the inner product, and the inner product is positive there.
Yes, because we are used to saying that if you have a signature, then dx with the gamma can be positive or negative, but that's not what's the
No, it's not the case.
that's not what the case is. That's why it is irrelevant.
Yeah, that's right.
Some other questions? If not, thank you again.